What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of harmful outputs generated by neural networks, particularly in generative models like large language models, LLMs. These harmful outputs can include copyrighted information, defamatory content, or actions that can be exploited by adversaries. The method, called short-circuiting with representation engineering, focuses on preventing the model from producing these harmful outputs by remapping internal representations related to such processes. By redirecting these representations towards incoherent or refusal representations, the method aims to robustly prevent the model from generating undesirable behaviors. This approach diverges from traditional defenses that focus on specific attack methods or input-output filters by directly targeting the processes involved in generating harmful responses. The goal is to make models intrinsically safer and reduce risks by removing their ability to produce harmful outputs, rather than just patching specific vulnerabilities or relying on additional training or filters.
How does the proposed method of short-circuiting with representation engineering work? Please illustrate step by step.
The proposed method of short-circuiting with representation engineering works by remapping model representations related to harmful processes, redirecting them towards incoherent or refusal representations to prevent the generation of harmful or undesirable behaviors in neural networks. The process involves two major components: datasets and loss functions. The training data is divided into the short-circuit set and the retained set. The short-circuit set contains examples that prompt the model's short-circuiting mechanism by yielding internal representations potentially leading to harmful behaviors, while the retained set includes examples that should not trigger short-circuiting to maintain desirable model representations. The representation rerouting loss is designed to remap representations from harmful processes to a desired target representation, while the retain loss maintains representations within the retained set by measuring the L_2 distance between current and retain representations. The rerouting loss can take various forms, such as routing the targeted representation to a fixed random direction with a large norm, or optimizing the short-circuited representation to be orthogonal to the original representation responsible for harmful processes. The chosen loss function aims to achieve a balance between robustness and preserved capability by directly targeting the processes involved in generating harmful responses. By remapping the sequence of model representations that lead to harmful outputs, the method disrupts adversarial control of multi-step processes rather than focusing on detecting attacks. This approach generalizes across diverse inputs that may activate harmful processes, ensuring coverage of a well-defined set of undesirable outputs without needing to identify all potential triggering inputs. The method is versatile and can be applied to virtually any neural network architecture, making it attack-agnostic and highly effective in preventing the generation of harmful outputs.
What are the theoretical or practical benefits of using the short-circuiting approach with representation engineering?
The theoretical and practical benefits of using the short-circuiting approach with representation engineering include: 1. Robustness against adversarial attacks. The short-circuiting approach with representation engineering significantly improves the alignment of large language models, LLMs, and enhances their harmlessness against a wide array of unseen adversarial attacks. It reduces compliance rates to harmful requests by an average of 87% with Mistral and 90% with Llama 3, showcasing strong generalization across diverse attacks. 2. Preservation of model capabilities. Unlike traditional defenses like adversarial training, the short-circuiting approach focuses on hindering harmful generations without compromising the model's capabilities. It achieves a minimal compromise in capability evaluation, with a performance dip of less than 1% in proposed tests, which is challenging to achieve with other defense mechanisms. 3. Efficiency and cost-effectiveness. The short-circuiting technique does not require additional training, costly adversarial fine-tuning, or the use of auxiliary guard models. It directly circumvents the ability of the model to produce harmful outputs by targeting internal representations, providing a more generalizable and computationally efficient solution compared to system-level defenses. 4. Attack-agnostic approach. The short-circuiting technique is attack-agnostic, meaning it does not rely on specific knowledge of potential attacks to defend against them. By remapping model representations related to harmful processes, it can prevent the generation of harmful outputs in a versatile manner across various neural network architectures. 5. Improved safety and security. By focusing on preventing the generation of harmful or undesirable behaviors at the internal representation level, the short-circuiting approach enhances the safety and security of AI systems. It reduces the risks associated with compromised outputs, such as generating copyrighted information or defamatory content. 6. Generalization across inputs. The short-circuiting technique does not require identifying all potential inputs that could trigger undesirable outputs. Instead, it focuses on covering a well-defined set of harmful outputs, allowing for robust prevention of harmful behaviors across a diverse range of inputs that may activate those processes. 7. Multifaceted applications. The short-circuiting techniques can be applied to prevent the generation of various types of harmful outputs, including private information, copyrighted material, or harmful agent behaviors. It offers a versatile approach to enhancing the safety and reliability of generative models like LLMs and multimodal models. 8. Fine-grained control over model behavior. By directly targeting the processes involved in generating harmful responses, the short-circuiting approach enables more targeted and fine-grained control over model behavior. It provides a method for internal control over external supervision, leading to more effective management of model outputs.
How were the short-circuiting techniques validated or tested in the experiments?
The short-circuiting techniques were validated and tested in the experiments by employing a comprehensive evaluation process. The experiments involved using standardized frameworks like HarmBench to assess harmful behaviors and a wide range of both black box and white box attacks. These attacks included gradient-based optimization, LLM optimizers, custom jailbreaking pipelines, multilingual attacks, system-level attacks, and representation space attacks. The models were subjected to various attacks such as pre-filling attacks, input embedding attacks, and rep-E attacks to evaluate their robustness against harmful prompts. Additionally, the models were evaluated on their instruction following abilities, knowledge and reasoning capabilities, visual chat capabilities, and multimodal understanding capabilities using benchmark datasets like MTBench, OpenLLM Leaderboard, LLAVA Wild, MMMU, and Berkeley Function Calling Leaderboard. The results of the experiments demonstrated that the short-circuiting technique, RR, significantly improved the model's robustness against harmful requests while preserving their capabilities, showcasing a strong generalization across diverse attacks and a minimal compromise in performance. The experiments also compared the short-circuited models with baselines and state-of-the-art adversarially trained models to highlight the effectiveness of the proposed method in controlling harmful outputs across different types of AI models, including large language models, multimodal models, and AI agents.
What were the results achieved with the representation rerouting (RR) short-circuiting technique in the experiments?
The results achieved with the representation rerouting (RR) short-circuiting technique in the experiments were highly successful. The RR technique notably improved the alignment of large language models, LLMs, enhancing their harmlessness against a wide array of unseen adversarial attacks, including embedding and representation space attacks. The RR method significantly outperformed standard refusal training and adversarial training, while imposing almost no penalty on standard capability. When integrated with additional model control methods to develop a Llama 3 to 8B instruct fine-tune, called Signet, the enhanced model exhibited a large reduction in harmful output by approximately 2 orders of magnitude, even when faced with unforeseen adversarial attacks. The RR technique demonstrated strong generalization across diverse attacks, reducing compliance rates to harmful requests by an average of 87% with Mistral and 90% with LLAMA3. The method eliminated the need for specific attack training and focused on hindering harmful generations, showcasing a Pareto optimal trade-off in performance. The short-circuited models showed high reliability against unseen attacks with minimal compromise in capability evaluation, with a performance dip of less than 1% in proposed tests, which is difficult to achieve with traditional defenses.
What are the limitations or drawbacks of the short-circuiting approach proposed in the paper?
The limitations or drawbacks of the short-circuiting approach proposed in the paper include the need for careful dataset curation to ensure precise elicitation of targeted representations. The effectiveness of the short-circuiting mechanism largely depends on the quality of the training data, which can be challenging to curate, especially for models with pre-existing refusal mechanisms. Additionally, there is a challenge in eliciting harmful responses from models with effective refusal mechanisms, requiring a well-curated short-circuit set that can bypass the refusal mechanism to trigger harmful processes. Another limitation is the potential need for hyperparameter tuning, such as the alpha parameter in the rerouting loss function, which can be time-consuming and require extensive optimization. Furthermore, while the short-circuiting technique is attack-agnostic and does not require additional training, it may still face challenges in generalizing across all potential inputs that could trigger harmful outputs, as it focuses on disrupting adversarial control of multi-step processes rather than detecting the presence of an attack. Additionally, the method's reliance on remapping model representations may introduce complexities in understanding and interpreting the model's behavior, especially in more complex neural network architectures.